everyone. Thank you so much for joining us today for a guest speaker session. We have with us Zhang. Xiao is a final year CS PhD student at University of Chicago, where he primarily works with Michael Mary on computer vision. His research is focused on unsupervised representation learning and generative model. The goal of his research is to develop scalable algorithms for representation learning applicable to real-world scenarios and complex image video generation. Today, he will be talking about his recent research paper, Residual Connections Harm Generative Representation Learning. Thank you so much for taking out your time, and I'll hand it over to you.
All right, thanks so much for the introductions. And also, I'm very excited to join this community and present my recent work here. So yeah, my name is Xiao. I'm a student from University of Chicago. So my research is primarily focused on the connections between representation learning and generative models. So today I'm going to primarily talk about my recent work that's try to connecting these directions. So arguably we have seen the prosperity of the generative models in the past 5 years. We see this ChatGPT, also the recent the DeepSeek has built a very generic AI tool for to assist our daily task, and also can answer some very complicated questions, and also even can reasoning about math. So in the computer vision, we also see this kind of progress, especially for the image generation and also video generations. So here I'm showing this images generated by the DALL-E, and also on the right I'm showing the video generated by the Sora, one of the state-of-the-art generative models. So we can see it can actually generate very high quality images, and it's so realistic. So there are multiple generative models, but in one words, basically it tasks the generative models generated training as kind of the predictions. So for example, in this popular autoregressive generations, so the task basically you have some data. For example, here we have the images, and we basically patchify it so that the images will be like split into some small patches. And so the task is that we take some visible patches, for example, showing in these orange blocks, and then to train a neural network to predicting the remaining parts, the patches highlighted by the green box. So one questions, and also this kind of a core topic of today's presentation is about what actually drives the generative models to make the predictions. For example, for this green box, so once we give this kind of context, the green box, so what makes this prediction happen, right? So as a human, we can see, if we are asking these questions, so we basically to check what's inside this kind of the orange box, right? Because we see it's images with some mountain in the far away, also some like tree, some water river here. So those kind of visual structures basically give the hints of like what's a possible context for this for this green box. So that means just like how human approaches this task, the general models internally also doing the similar thing. So what essentially is basically trying to project those kind of visual input to some high-dimensional space, which try to reason about these connections of the patches in using some visual representation. For example, here, for this target patches, it have some part of the rock. So to make this prediction happen, you have to reason about this kind of there is a pile of rocks here. So that's the model computer connection to predict this. Also for the river, because we see a rivers in these patches, so basically the model can use these cues to make this prediction. But even more tricky, you can see there's some shadow here. This shadow basically indicates some reflections of the trees here. So basically, I have to reason about this kind of broad range of visual structures to make a prediction happen. So in that case, to training a model that generated high quality images, essentially equivalent to that, we are basically asking a model to understand the visual representations. So in other directions, it's if the models can learn a better representation, does it also imply the model can learn image generations? So basically, I'm asking I would try to answer these questions in this new paper. So to give some feedback, to give some background of what's the happening in the visual representations. So there are kind of two popular topic. One is called the discriminative approaches. So essentially, it's driven by learning with image crop. So what it do basically, it take a image crop, take image and generate two random crop, and then train an encoder to map those crop into some shared space. So the idea that it basically asks the encoder to find some shared pieces of this image crop. So which usually are kind of high-level representations. But the downside of that, it doesn't have a, for example, a generator or decoder to map this representation to this pixels, but actually learn good representation so that we can apply it to, to do some real-world analysis. We can, for example, here we can apply the models on this this driving data set and to do the recognition of this scene, for example, can recognize the car, people, and lines. So basically assist our daily activity. So on the other hand, the generative models essentially is driven by this kind of denoising autoencoder task. So the idea is that we have some images. So instead of to create some crop, we crafted images using either, for example, dropping some pixels or adding some Gaussian noise to it. Then we train a denoising autoencoder, try to remove this corruption, or equivalent, we can see that's basically try to reconstruct images. So through this task, the model have to reason about the visual structures. So it learns some useful representations. But despite we have put so many efforts recently to study the generative models, we have built very big models for generation tasks. But actually, there's a huge gap in terms of representation qualities between the general model and discriminant models. So here I'm comparing two most representative models, MAE for general models, the MOCO for discriminant models. So you can see the accuracy, which basically evaluates the representation of the ImageNet 1K for classifications. So you can see there's a clear gap, especially for the k-nearest neighbor accuracy. The gap is roughly 40, which is huge. Also, there's some substantial gap in the linear province. So there's a huge gap between two models. Basically, we are asking, so what makes that, what actually happening, and what prevent the models to learn a better representation? So to understand this, we can firstly to visualize what's happening in the general models. For example, here we take a pre-trained general models and to take the encoder part of it and to visualize what's been learned in the encoder. So here we're basically using some like compression approach to compress the high-potential features into some like street channel and visualize as RGB images. So basically the similar color indicate the model think the similarity of the two pixels in the feature space. For example, in the model's little space, the model think the little girl and the bush and also the umbrella, they have some like similar color. So that means in the embedding space, the model think those three things are similar. But we know that they belong to three different categories. They should be like encoded set into different colors. The clear model doing something incorrect here. Also, another thing that you can see there's some shadow in the background here, in the ground here. So which also represent as the magenta color here, which is different from this ground without shadow. So that means in the feature space, the model think the ground with shadow and the ground without shadow are they're kind of two different things in the linear space, which is which valid our human understanding because those are all belong to the high level category ground. So that means the model is focusing on this kind of low level details, but lacking some like high level understanding. And so my paper basically tried to tackle this problem through this architecture design. So in the past, the residual connection has been the golden standard for the network architecture, right? So the residual connection basically proposed to solve the problem of gradient vanishing. So it basically introduced a kind of skip connections. That basically they will build some like shortcut that directly transmit the signal from the input to the output. So if you think about it, so essentially this highway will solve the gradient vanishing problem, but also bring another problem, which, whatever the low-level informations from the data will directly propagate to the end. So that means in the features, which you hope to learn some abstract feature to be invariant to some low-level details, actually the information out there. So the model has to do a very hard task to remove it. So eventually the model, it doesn't do a good job to learn good abstractions. So if the residual connections is an issue, so can we simply remove it? That will bring us back to before 2015, before the inventions of ResNet. So we get the feed-forward network, which is the backbone for the VGGNet, AlexNet. So we know it has, a gradient vanishing problem. So it cannot, we cannot train with a big, deeper network because the gradient will vanish. So, but let's just put that downside aside to see what's the benefit of the feed-forward network. Actually, there are some recent work studying the behavior of the feed-forward network. So one work from the Aurora's group showing that if we abstract, the whole network as the feed-forward network, where each layer is some polykinetic layer. Each layer is essentially a VIT matrices denoted by WL. So the whole network can be approximated as the dot product of all these VIT matrices, which essentially a big W matrices. So the whole network can be analyzed as a single VIT matrices. So in this study, it showed that the singular value of the big W, the big matrices actually have this property that the singular value of the W is decreasing over training. And also, if you have a deeper model, so that means you stack more layers. So the singular value will decrease much faster. So that will indicate that feed-forward network has some implicit, regulation built in, which means the rank of the output will become lower over training. Okay, so if we think about another architecture, network architecture, which is the attention modules. So it basically have these operations. So you have the Q, K, and V, which have this following format, which sharing this very similar formulations as the classic. Share with very similar format of these classic mean shift iterations. So there's some reason we're showing that these operations in the attention block, if you remove the skip detection, actually it's guaranteed to convert to this one rank structure, another low rank regulations. So in both cases, removing this kind of skip connections will bring the benefit that the output will just have some low rank structure, which indicate, go back to the image structures, that will indicate the model will ignore some low level details and focusing on the abstract features, which is great. But if removing that will bring the curse, we cannot train big models, but the whole thing about recent developments of AI, essentially we have a scaling law. We want to train bigger models. We want more parameters to have a better performance. So this clearly violates this kind of the trending. So what do we do? Actually, our solution is very simple. We know the residual connection is great. Also, we know there are some benefits of this feed-forward network. We just combine the best of both. So what do we do here? We still have the residual connections, but we add some weight decay factor, alpha. Alpha is basically a scalar per layer. If you have L, so for each layer, we have a alpha L, which is the value between 0 and 1. So if alpha is 1 all the time, that means we recover the residual connections. And if alpha is 0, we have feed-forward network. So in our design, we gradually decay the alpha, so that it starts with 1 in the first layer, and then gradually decay to some value. So we use very simple decaying factor, a linear decay factor. So basically, it's linear decay the alpha over network depth. So basically, the network will initially behave like residual connections, have this preserve much of gradient, and gradually in the bottleneck, it encouraged to learn these abstract features. there's no introduced extra parameter, just simple alpha decay factor to the residual connections. That's it. That's our whole design. So if we apply it to the general models, we can see the feature it learned actually shows much more semantic abstraction, some like very clear contrast. For example, if you see the little girl, basically all the color are similar. So that means in the latent space, model thing, the whole girl are, all pixels of the girl are similar. And they're all different from, for example, amber, the bush. And also you can see the shadow on the ground. There are no difference between the ground with shadow and without shadow. So that means the model kind of successfully ignore, this kind of effect of the shadow, which is pretty useful for example, in self-driving, where you want the feature to be invariant to the extreme weather conditions. This is basically an indicator that the model learned a useful feature for that purpose. Okay, so to give some like concrete analysis of how good our introduced decay residual connection is to the downstream applications. So we use this standard benchmark called linear probbing. So the idea that we take the features of the general models and we then train a linear classifier on top of it and to solve the image classification task. So we're showing this analysis across different models, including muscle encoder, including diffusion models. We also try different sizes of models, including VIT base or VIT smaller models. So here we're showing the results of like use the model with standard residual connections, which showing the gray block, and also the model with the decay and then the shortcut with showing in the blue box. So clearly, we can see the huge improvement compared to a baseline. And also, we show even in the diffusion model, which is another popular of image general models, we also see the similar improvements. And also in the large data set, for example, in the ImageNet 1K, which is standard benchmark, we see 5% improvement, which is huge in terms of we don't introduce any parameters. So because like previously we were talking about the connections between the connection and the rank. So we're actually showing here our design actually encourage lower rank. So here we are measure the feature rank using what we call the effective feature rank. So you can think that's kind of soft measurement of the rank of the actual feature rank. So we can see here our design promotes kind of low rank representations. And finally, we show the improvements of the feature learning capability in the diffusion model actually translate into the improvement of generation quality. So here we measure on the generation task on the ImageNet, and we measure the image quality using FID. Lower the better. So we can see there's also a huge improvement in terms of qualities. So that means we have this kind of simple design that doesn't introduce any normal parameters that have the consistent improvements in both generation task, also like in this representation learning capability. So we also do more analysis. So we apply our methods to different model configurations. So here on the left, we show the models with different channel dimensions. So we can see a consistent improvements across all this kind of configuration starting from 348 to 1024. And also if we scale with model layers, we can also see the similar training. So that means our method can also scale with bigger models, which indicate a broader applications for our bigger models. So we also do another analysis on the alpha. So basically, alpha mean is the hyperparameter we choose that define the decay rate to all the final layers. So because we have a linear decay rate, so the alpha mean that's only hyperparameter we introduce in our design. So we applet over different choice of alpha min, starting from like 0.6 to 1. 1 is essentially the baseline. These are standard residual connections. And we are showing here, our design is basically very robust to the choice of hyperparameters. Basically, you can choose 0.6, 0.7 for most of configurations. And what's interesting here, if you compare this design, the transformer with 700 channel dimension with 12 layers actually have the better performance than the model with 24 layers with 1024 channels. So that's a clear like advantages of this kind of design in terms of compare with bigger model. So that means, with some like proper regularizations of the models, actually the smaller model can outperform the bigger one. So basically, that's basically I want to use this to call into question, does the scaling law is the only direction to pursue? Because like this kind of regulation clearly indicate, there's alternative way where, because if the goal of the generative task is to improve the model's recognition ability, feature learning ability. So maybe it's better, it's more like economically like advantage to think about, how to build some like extra recognition over the model so that it can have a better feature learning quality and also generation quality. So we also have the analysis, different decaying configurations. So here we're comparing two networks. One is that we only decay on the, we don't decay on the residual connections. We decay on some like blocks. And those are learnable blocks in the network. And we show, actually, it doesn't introduce any significant improvement. The reason here is that whatever the decay you put to learn a module, the module would learn a factor internally to counter the effect of decaying factor. So like if you decay the contribution f by this factor, so basically it will learn 1 over this factor inside the models, so that it can counter the effect. So another thing we compare is that if we put the decay factor to both block, so it actually have a similar performance to have a decay factor on the X or the residual connections. So that indicates the primary contribution actually is decaying on the residual connections, right? Not the learnable blocks. So on the right, we are comparing with more configurations. So because our simple design is the linear schedule, linear decay of the alpha over network depths. So we also try a more sophisticated decaying scheduler, which is cosine scheduler, where we don't see much of a difference. And also we also try a learnable alpha, so that instead of have a fixed scheduler, we treat alpha as some learnable parameters. So that's basically resemble the design of the heavy network. One of the work that before the ResNet, but also like studied the behavior of the residual connections. So we show actually it's give a slightly worse performance. So I think this because in the learnable setup, there's no pressure so that the model learn this kind of smaller alpha, because like to make the optimizations better, the model will prefer this kind of the contribution of the skip connections to be amplified, so that will provide much more better gradient signal for these for the loss. So without any regulations, it doesn't learn the correct low rank patterns. So that basically that's one reason why our design is better than learnable modules. Okay, so here are some validations on the image generation task. So we compare our design with the standard residual connections. So that standard residual connection is on the left, and our design is on the right. So if we compare the image quality, essentially we are make the object correct. Here you can see the dog face. Actually, it's basically some random pattern here, and also the dog here has some weird black block on the head. So those filter mode indicated the general models doesn't actually understand the image structures, which cause this filter pattern in their generated images. Here is a more visual edition of the learned representations. So here we show in the middle we show the the visualization of the standard residual connections, and on the right we show the visualization of our learnable decay factors. So with our decay and then the shortcuts, so we see our model actually to learn a more abstract features and also have some like a global consistent semantic pattern. For example, here all the human are colored by the yellow, so that indicate it's universal thing. All the human are have a similar representations. Also here in this in these images, you can see it is two people standing in front of kind of complicated background. In the standard residual connection, it basically messes up everything. It doesn't like there are no clear object pop out from the embedding. But here we can see a clear like associations of the human, also there's the model cycles. Yeah, so it's doing great on all this kind of recognition task. So to summarize, so we introduced this kind of reduced identity shortcuts, which like add a simple decay factor to the residual connections, which encourage the low rank feature at the end. So this simple design doesn't introduce any learnable parameters, but improve the representation quality of the general models and also improve the generation quality. So if we compare our design with with the baseline also this kind of state-of-art contrastive learning method, we show our representation quality, especially in the k-nearest neighbor, it's very closer to the discriminant models, and also show a significant improvement of the baseline. So I will pause here, waiting for any potential questions.
Have you experimented with other ways of making sure that even though gradient pass through the skip layers, but skip connection, but the information does not pass through, other than scaling it out?
Sorry, can you repeat that?
Did you try any other ways to make sure that the information does not pass through the skip connections?
So I think the choice is very limited. So either you remove it or you decay it. So I'm not sure if there are other approaches for that purpose.
Have you tried using event-based camera images instead of regular images?
I see. So so it's not that common to learn representations or to generate images using the output from event-based camera. I think those are more suitable for the for example from the detecting some subtle motions, some like a quick change of the video. I think that's a good suggestion, because I think we also plan to apply our method to the video, but we haven't tried, because I think video.
I think you should consider event-based cameras differently. Motion is a derivative. Their focus is on pixel intensity.
Yes.
So to me, it appeared your method was parallel, if I can use that word, or complementary in some way. So I'm sorry, you're correct, but if you change your perspective to pixel intensity, I think you have a great opportunity there, in my opinion.
Yeah. Also, I think that's a good point. Also, another point I want to highlight that the video compared to the images are much more redundant. They have rich information in the spatial axis, but redundant in the temporal axis. So that means for the video, you want to encourage more like abstraction compared to the image-based model. So that's why we see in the recent developments, the representation learning in the video actually underperform the image-based representation learning, because you need much more compression rate. So that's where our method could also potential to bring further improvements. But yeah, I think like this argument on this kind of pixel intensity of event-based camera, I think that makes sense. Thanks for that.
Oh, you're welcome. I'll reach out to the Cohere folks in Toronto about that to see if they've got any interest. Thank you.
Okay, thank you so much. Okay. If there are no further questions, I can keep going. Okay. So
What do you think?
sorry. Mhm.
What do you think about adding noise in the skip connections to
Oh,
interfere with the transfer of information?
yeah. So actually, we try that. But the thing that the models have the flexibility to counter whatever the recognition you put on network. So that means if you add a noise, for example, you use a fixed standard deviation with noise, the model will try. What the model strategy is try to increase the feature norm so that it makes your noise to be basically effectively downweight the contribution of noise because they have a much bigger vector, but that will actually effectively remove the contribution of noise. So the model will actually learn to counter on the noise you add, unless you have some other regulation. For example, you want to penalize the norm so that the model doesn't like pick up this kind of as a cheating strategy. But it doesn't. But in our experiments, we find actually adding noise doesn't really help in terms of the representations. Actually, it makes the performance worse.
Oh, interesting. Thank you.
Thank you. Thank you. Okay. So yeah. So this paper is primarily focusing on how should we improve the visual understanding of the general models. So because of this image quality and the visual understanding, they're highly correlated. So recently, I'm also exploring another directions. If we have a better visual understanding, does it also help improving the generation qualities? So that this is our recent work to exploring these directions. I will quickly go through it. So basically, in this paper, we're considering a hierarchical generative models. So we have set of diffusion models that operating at different hierarchy. But this is different to the recent, the hierarchical model which operating on this VIT pyramid or image pyramid. We are directly operating on some semantic hierarchy or semantic pyramid. So what we do here, we use some pre-trained visual encoder, clip, dyno, whatever the visual encoder give you some like good representations. So we use some like trick to patchified images into smaller patches. So then we fit each patch to the encoder, so that by reducing the size of patch, the encoder has very limited context of the visual structures. So that means if you reduce the patch size, the encoder can only give you some like lower or finer grained structures. And if you feed entire images, it gives you some abstract features. So if we using this kind of trick, and we can construct this kind of what we call semantic hierarchy over different level, and then we train a set of diffusion models that try to generate those feature vectors. So essentially, you can view this kind of whole generation pipeline is that you firstly generate some high level features and condition on that to generate the feature at more like a little bit detailed level, and then in the end you get images back. So it's very simple. And so one immediate benefit that we have controllable generation, so that we can share in some part of semantic feature and try to ask the model generate the rest. So we can see actually we can control the image qualities, image content, so that different images have some shared semantic structures. And also another like property we are more interested in is like does this design improve the generation qualities? Actually, the answer is yes. So we compare our models, our 5-level hierarchical models, to some very big models, some like state-of-the-art diffusion models. We see our model trained with fewer iteration. We only train 500K compared to the model trained with 7 million steps. And also in terms of the computation budget, we're using a quarter of it. 34 versus 118 flops. So we actually achieve the similar image quality. And also compare in the unconditional generation task, where we don't have the image class as conditioning, we show a huge improvement in terms of image quality measured by FID. And also we want to highlight that our models, without any condition, actually achieve the similar performance to the state of art, the huge models with conditions, but but use fewer budget, and also we run in unconditional mode. So in other tasks, for example, in the task to image generations, we show our method using just very few parameters and just very limited data actually achieve similar performance to the gigantic 7 billion parameters model in terms of image qualities. Yeah, so because I don't have much of slides for this paper, but if you're interested, please to search for this title called Hierarchical Diffusion Model using Hierarchical Latent Prior, which is on arXiv.
May I ask a question?
Sure, go ahead.
Have you tried converting it to black and white and then coloring it later?
So what do you mean by black and white?
Well, going to grayscale.
Grayscale, I see.
And then doing your analysis and then adding back the color.
So you mean for the generation or for the residual connections paper?
The connections paper. Well, for both, but really the connections is, I think, easier.
Oh, you mean this paper?
Yeah. Well, for both papers.
So okay. So please clarify me. So in this case, so what's the purpose of to convert input to grayscale? Because that will lose some information. Sometimes the color could be useful for recognition, and losing that could like harm the model's capability. So what's that? Is it application that's required the input to be grayscale?
Okay, so I'm thinking about the event-based stuff.
I see.
So probably the other paper. You could do for both, but probably the second paper. Yeah. Thank you.
I see. Yeah, I think because the method is generic, it doesn't assume the specific format of data structure. I think it should be generically useful for all the visual data, video, event-based camera, grayscale. Because we don't really hack, we don't really require the input to be, RGB channels. It's the only difference here. For example, in this case, you want for generation, maybe you want some encoder that handle the grayscale or event-based camera to start with. But for the residual connections, I think because it's trained from scratch, it doesn't require any labels, any supervision. So I think you can directly apply to whatever data format you have. I think it should generically helpful. I think that's a good point to think about other data modality, and thank friends for raising that up. Thank you. Okay, I think that's the last slides of today's presentation. So I'll stop here for more questions.
I have a question. There are the architectures like UNet where you have like very long residual connections so long.
Yes.
So in those cases, how do you think that this decay factor should be added?
So yeah, so in our paper, we actually tried the diffusion model. So this diffusion model is actually a UNet structures. So what we do is simply to decay from the input to the end. So if you like flat the UNet, basically lay out the layer by depth. So we also like decay from the first layer to the end layer. So the final layer we have the most like decay, and we just treat as standard network. So which also like improving the both representation quality and also the generation quality. Yeah, so those are with UNet design.
Got it.
Thank you.
There's a question in chat as well. Is the training course out?
Okay. We haven't, because this paper is being under review. So we will plan to release the codes once the paper accepted. But It's pretty straightforward. You just take whatever network you have, just add this decay. So linear decay from 1 to some predefined alpha min, and that's it. You don't need to change anything else. So one thing we noticed that it doesn't really compatible with the, for example, the supervised task, because the supervised task is kind of different, because for example, for supervised classification, so we know what the label, ground truth label for the images. So the task for now we're essentially just using whatever the computing power you have to minimize loss for that ground truth target. So this is very different from the unsupervised learning, because for unsupervised learning, the essential is basically to search for some like features with some like property, which is low rank, or abstract, which is clearly one of the primary target for self-supervised learning. So that means if you have a clear target, you don't need decay. You just use whatever over parameterized network fully full bandwidth residual connections to do the optimizations. But here for the generative model for unsupervised learning, you want that decay to make it work. Yeah, thank you. Thanks for a nice comment. So if there are no further questions, and I think I will stop here. And thanks for everyone for attention, and thanks for joining.